Hello everybody, this is Mr. Johnson and I'm going to be going through the new notes for this chapter. The letters for this chapter are PM, probability models, and it's related to what we just did with probability. In order to get started, we're going to play a quick game. It's called the game of greed, and it tests your ability towards continuing to play a game even though the chances of winning might change as you go on. So it deals with probability. So the first roll, it's played with a single dice. And usually the teacher's going to roll it. There's one person rolling. A game is consistent of 2 rounds. So it's like a college basketball game where you have a first half and a second half. And your total score for the game is the sum of your 2 scores. So here's how it works. Everyone in the classroom is going to stand up. The teacher's going to throw the dice, and whatever value is showing, you're going to write down on the chalkboard. So I've come up with a couple of examples here. Let's say that we've rolled a 1 here on our first toss. That's fine because the whole goal of greed is to roll anything except for a 5. So if you're happy with this score of a 1, you can go ahead and sit down and you'd record that total over in your box. You've only rolled a 1. Now we don't know what we're going to roll next. So if we rolled a 1, then we roll again, we could maybe get a 3. We haven't rolled a 5 yet, so we haven't lost. If you're happy with 1 plus 3 as your total, then you would sit down and you'd write your total over in this box. So you'd write 4 over there. If you aren't happy with 4 and you want to keep trying your luck, you'll toss it again. Maybe you'll roll a 3, toss it again, maybe roll a 6. And as you keep on going, people usually start sitting down because they don't feel as comfortable thinking that they won't roll a 5 on the next turn. And they want to keep as high of a score as possible. So you'd add 1, 3, 3, 6, and 1, and that would be your total score over here. So let's say we kind of played this game, and we kind of came up with this set of results. So you chose to stop at the 1 that's out here in our first practice round. We would have missed out on the 2, but that's okay. At least we weren't like the greedy people who stuck around and ended up getting a 5 and lost. So if you had gotten a 5, you would have written a total of 0. But I add up those numbers and I get 14. So that was a practice round. We're going to play 2 real games right here and right here in order to add up those scores and put them in a stem and leaf plot. So the example here, I have a 4 and a 5. Well, I stuck around and I got a 5, so I lost in the end. My total score was a 0. But I still have the second half of the game, which is round 2. So as I was going, I rolled a 6, a 3, a 4, a 1, a 2, a 6, and then another 4. I chose to sit out here. I missed out on some of these rolls, but that's alright because I didn't lose everything by getting a 5. So my total for that second round was a 32. If you add those up, you get 32, and I would have to place that in my stem and leaf plot, 3, 2. Alright, notice the first game is over here on the left, the second game is over here on the right. So this one has to be backwards, 32. The stem is in the middle. If I go to the second game, which is down here, usually people understand it a little bit better, and so they're willing to take maybe more risk or play smarter and not take some risks. So in this first one, you can see it 2, 2, 2, 4. I chose to stay on the 4, which is good because the next roll would have been a 5 and I would have lost. So that adds up to a total of 10. Then, in the second game, it went 3, 1, 5. I happened to stick around for the 5, and so I lost, meaning my total was 0. If I add those up, that's 10. I need to put that up here in my second round, so 1 with a 0 would be 10. So after you play, you should go ahead and graph your 2 scores over here on the first round and the second round. Everybody in the class should be putting their number up here on the stem and leaf plot. So if you counted up these, I believe there would be 20 different students who played and had different scores for the first game and then different scores for the second game here. Were there some strategies that worked out better than others? Okay, if you played that second game, what were you thinking? What was the strategy involved with that? Statistically, a 5 is usually going to be rolled within 6 tosses. So it has a 16% chance of showing up, and that will happen usually on the 6th toss or before the 6th toss. So if you make it further than 6 tosses, your chances of continually rolling good values start to decrease. So like up here in the second round of the first game, 1, 2, 3, 4, 5, 6, at this point in time my odds really start to drop off. And you can see we went for a while, but we ended up getting a 5 eventually. So the odds of getting all the way out to the 1 is very, very small. If we look at F, did your experience pay off in the second game? Well, looking at the different graphs over here, definitely more clustered, and actually clustered at smaller stem values, so like 0, 2, 0, 8, meaning 2 points, 8 points. Whereas the first game was spread out. It was a little bit more skewed, and actually some people might have won a lot more just because they had higher values, they stuck around for longer. So 44 points versus the other point. So that's just kind of a sample. Your class might not have the same data because everybody would be playing a different game than I just made up. So if we kind of look at that, the experience in the first game for my situation didn't really pay off in the second game because unfortunately we didn't get that long run of numbers. Everyone in the second game is kind of clumped together, all right, centralized here around 8 or 9, whereas the first game is a little bit more skewed out, and that's partially because the first game had a long run of numbers and people sit out at different points. So that game kind of gets us into the idea of what we are doing. We are taking different probabilities, different likelihoods, and we're putting them together in a graph and seeing what shapes we get out as a result. If you look at the bottom of the notes, we talked about the answers last chapter. In this chapter, we're looking at those answers to see if there are any patterns. How do they occur? Are there shapes to those patterns of answers? If you've done the casino project over the last few days, you've actually seen this in action. The casino project deals with craps, and the odds of rolling different combinations of dice are right here. Usually we are concerned about the diagonals. Now this actually shows up when we start to graph the likelihood of rolling maybe a 7. There are 1, 2, 3, 4, 5, 6 different options here. So 6 out of 36 creates this kind of tall bar. If I look at some of the other options, like maybe rolling a 2, it doesn't happen very often. That's actually why it's one of those very high-paying bets. It only happens 1 out of 36 times, so it would only go up a tiny amount. Rolling 3s, rolling 4s, rolling 5s, they all start to occur more and more and more until we get to the option that is the best option, 7. Now, why do casinos play that 7 loses? Well, because they're not idiots, and they know that this will happen the most, and so that means it has the best odds of making players lose. This is the idea that we are going to be focusing on in this chapter, visualizing the patterns of unique probabilities. So on the next page, let's go ahead and let's introduce our first vocabulary word, our first definition, a probability distribution. That word distribution literally just means graph. It describes all of the possible outcomes of some chance process, and it usually puts that in some visual format. So we can see, just like on the last problem with the craps outcomes, there's a pattern to what's happening. So we're going to start off with an example, such as determining the sample space for tossing a fair coin 3 times. If we write that out, starting at one of the extremes, tails, 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 and working towards the other extreme, heads, 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 there are going to be 8 different options. Tails, 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 heads, tails, heads, tails, heads, tails, tails, and so on and so forth until we get back over there. Now you could figure out if you collected or written out all of the examples by using this nice little formula over here. So coin has 2 options, and you are tossing 3 of them, or you're doing it 3 times in a row. So 2 to the 3rd power is 8 total. And we have 1, 2, 3, 4, 5, 6, 7, 8 options, which means we didn't miss anything. The odds of getting tails, 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 it's 1 out of 8. The odds of getting this one, also 1 out of 8. 1 out of 8, 1 out of 8 for all of them. So if we define a variable or an outcome and we give it a letter, x, and we want that to stand for the number of heads that we are obtaining, that's going to vary. So in this first column, I didn't have any heads, 0 heads. All right, so that only will happen 1 out of 8 times, which as a decimal is 12.5%. If I look, having a number of heads, I could have 1 head. So that would stand for this column. There's 1/8, 1/8, and another 1/8, which makes 3 of them total for a 37.5% chance. If I wanted to have the options that result with 2 heads, 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 tails, anything like that, there are again 3 of them. 3 out of 8, which is 37.5%. And then the very last one here, if I get 3 heads, everything is a head. That doesn't happen often. It happens 1 out of 8 times, which is a 12.5% chance. What happens if we try to summarize those answers right down here into a graph? Well, if we put that together, we are literally getting a probability distribution. We're getting this graph. You can see if we roll a value of 0 heads, that happens 1 out of 8 times. All right? Not very often. If we get 1 heads, which would be right over here, that's a little bit higher. 1, 2, 3 out of 8. Same thing with rolling 2 heads and then rolling 3 heads, which was heads, heads, heads. Doesn't happen very often, only 1 out of 8 times. So we get this kind of shape here, this symmetrical shape where the middle happens the most often. Now, does this table add up to 100%? If you take those and add them up, you get 1, which again, 1 means 100%. We didn't miss anything. We have all 8 total options. There aren't any more. Now, kind of a special note here. This is symmetrical. These are kind of special problems. Not every problem that we will do will be symmetrical, but they're the easiest cases because they're special. So that's what we're going to start off with. So the next idea, a random variable. That's what takes the numerical value that describes certain outcomes. We just talked about that, like it could be the number of heads that you flip out of 3 tosses. So it's basically representing an idea as a letter where we could have multiple outcomes, not just one outcome. It could have been maybe 1 head, or maybe it could have been 2 heads, or maybe it could have been 3 heads. That's why we have to use a variable, because this result can change in different circumstances. Another example would be like the number of people in line at a cash register at 1 p.m. We could have 0 people. Maybe we could have 1 person or 2 people, or maybe we could have 22 people if it's a really busy day. So that variable could change, but this idea in here is one idea. Very last one that I wanted to give you an example of would be P, the probability of this event happening. A specific person eats the next cookie, so maybe Tim really loves cookies, and so the odds are higher for Tim, whereas Sally wouldn't, and it would be smaller, but it could be probability of Tim or the probability of Sally. This will change based on the problem or what we're looking for. So let's look at problem number 2. A life insurance company sells a term insurance policy to a 21-year-old male, and it pays him $100,000 if the insured person dies within the next 5 years. The probability that a randomly chosen male will die each year is found in what's called a mortality table. Now, real insurance companies use mortality tables, and they are very big and very complex based on a lot of different factors, like if you smoke, or your age, or your prior health risks, all sorts of things, but it helps them decide who they should insure and who they shouldn't. This is obviously a pretty simplified version down here at the bottom. So the company collects a premium of $250 each year as payment. So when you sign up for insurance, you have to pay money for that insurance. And for this guy, it's $250. So we're going to let this random variable be the amount of money that the company earns. Now that's important. We're not thinking about the person, we're thinking about the company. So the company makes $250 per year, but that's only if the insured person doesn't die. Now they actually have to pay out or subtract the $100,000 to the family of this person if they die in that year at that age. So the relevant mortality table here is missing a piece all the way at the end. All right, so let's kind of look at what's happening. The age of the person at death and the likelihood that they will die. So at 21 years old, there's not a very high likelihood of them dying. It's actually, if you move the decimal, 0.183%. So it's about 0.2%. Not very much. If we move to the age of 22, that actually has gone up a little bit. It would be 0.186%. And it keeps on rising, keeps on rising, and keeps on rising. So each of these values gets progressively higher as they get progressively older. But we don't make 100% if we add all of those things up. So in order to make a legitimate probability distribution, we have to find that missing piece. So in your calculators, you would add up all of these numbers, and then we'd subtract that amount from 1. When we do that, we get 0.99058. Now, if we make it to this box down here, the company doesn't actually have to pay him the $100,000. This is just a 5-year policy. All right, so it expires after 5 years. They don't have to continue it. He would have to sign up for something different. And if we think about that percent, that's saying that 99.058% of their people will make it through the age of 25, and the company won't have to pay them $100,000. So that means about 1%, a little bit less of people, will have to be paid this amount because they die or something happens. And that's why people get insurance, is so that their family can be paid a little bit of money and have some security if they pass away. So why do those probabilities increase as their age increases? Well, the simple answer is the odds of a person dying increase as they get older. Since they're young, the chance is still pretty small. These odds would change, obviously, if you were talking about somebody in the 40s or 50s. They'd be probably higher. So let's construct a probability distribution for X. X meaning the amount of money the company earns, all the way back up here in this part of the problem. So if we're thinking about the company, if we are looking at someone who's 21 and they've only paid their due one time, that's $250 that the company has earned. But if they died at the age of 21, the company is going to have to pay them or subtract the $100,000. So if you take the $250 that they earned and subtract the $100,000 that they had to spend by paying this family, you're going to have a loss of $99,750. So the company is not doing very well if everybody they have dies at the age of 21 and they've only collected $250 from each of them. That's bad because they're losing a lot of money. It is nice though because the odds of people dying that early are pretty small. So if we think about the next column, when they were 22, they would have paid their due of $250 twice. So think about 250 and 250, but then you have to subtract the amount that they're paying this family, so that is negative $99,500. Moving on to the third box, we need to continue with that trend. So by this point in time, he will have $750 that has been paid, okay, and this is paying to the company, but if he dies within that year, you still have to pay out the $100,000 to his family. So putting those together is negative $99,250. They're still losing money. At this point, they would have credited $1,000, but paid the family $100,000. So that is negative $99,000. The last year of this policy, because remember, it only goes for 5 years, it only goes out this far, they will have paid $1,250, but the company loses $100,000. So that is negative $98,750. So the company is losing money if these people die within 5 years. But a majority of people don't die within 5 years. In fact, 99% of them live to be 26 or older. And if they live to be 26 or older, that means they've paid for 1 year, 2 years, 3 years, 4 years, 5 years. And this company hasn't lost a thing because they don't pay them the $100,000 if they live to be that age. So they make $1,250 in that case. So they are up. They are up a majority of the time, and they are down a small minority of the time. If we move to the next page, we come to our next vocabulary term. It's a really important idea that's going to come up throughout the chapter. It's called the expected value. The expected value of a random variable is found by multiplying each possible value that could be produced by its probability and then adding up all of those numbers overall. It's also called the mean sometimes, or a little bit more accurately it would be called the weighted average. If something has a better chance of happening, it's going to have a little bit more weight to it. An example to show this with question number 3 talks about a lottery. So most states and Canadian provinces actually have a government sponsored lottery, and it's kind of a simple wager for the tri-state pick 3, and that happens in New Hampshire, Maine, and Vermont. So you choose a 3-digit number, and the state chooses a 3-digit winning number at random and pays you $500 if your number is chosen, which seems like a pretty good bet. You know, maybe you would actually do that once a week, and maybe you would win. But think about how many possibilities there are. If you work them all out, you could go 0, 0, 0 all the way to 9, 9, 9. That is 1,000 3-digit numbers. So when you are guessing one of those numbers, if you buy one ticket, you have 1/1000th of a chance of winning. So let's go ahead and let's make a random variable here, which X is the letter we're going to use to stand for the amount of money your ticket will pay you. And let's see what the probability would be, or what the expected value would be. If you look at this table, we can expect to win $0 999 times out of the 1,000. It's only that one correct number that will earn you the $500. So if we need to find the expected value for payout for the whole lottery, we need to take the value times its probability. So that's $0 times 0.999. It's really weighted of paying out $0. And then we're going to go ahead and we're going to take the other outcome, which would be paying $500. They actually win, but that only happens 0.001% of the time. So that is 999 out of 1,000 versus 1 out of 1,000. And you can see the weight is definitely with this piece over there. If I work it out, I get 0 plus 0.50. So that is 50 cents. Okay, because this is talking about the number of dollars. $0 versus $500, and we get 0.50 dollars, 50 cents. So if you were going to be selling those tickets, you probably wouldn't want to sell them for anything less than 50 cents. You would be losing money, because if you bought a ticket every single day, you could expect to win on average 50 cents over the long run. It doesn't work every single time for a single run, but over the long haul. So the ticket cost, you'd probably want to sell it for over 50 cents, probably $1, maybe even $5, and then the states would be making money that way. So again, this is the expected payout. This compares a little bit to the regular average. If I take the regular average, so you can win either $0 or you can win $500, and I divide them by the number of choices, I would get 250. But it's not that on average people would win $250, because these two options are not weighted the same. $0 is weighted much more than the $500. You lose much more than you win. So that's why we have to do this expected or weighted average. So with question number 4, what's the expected value of the amount the company earns on its term life insurance policy from the earlier example? What does that mean in terms of the context? If we go back to that problem, we can see the different payouts and their probability right here. So finding the expected value takes the probability into account. Now, most of the time, you're going to fall in this last category, 99% of the time. It's very rarely that they're going to actually lose money, that that person is going to die before they're 26. So we're going to have to go ahead and take all of these numbers, the values that they would pay, times the probability. This value times this value, this times this, plus this times this, plus this times this, and then very last, this times this, and we add all of those up. Back at question number 4, it would be negative $99,750. That means they're paying that much, times the probability that goes with it, 0.00183, plus the next payout, negative $99,500, times its probability, 0.00186, plus next payout, negative $99,250, times 0.00189, plus plus negative $99,000 times 0.00191. Continuing on to the next line, plus negative $98,750. This is that last box before the insurance expires, times 0.00193. Then we'll go ahead and add the part where they actually would make $1,250 times its probability, 0.99058. So most of the time you're going to land right back there, but we should expect to make whatever this answer is going to be. If we're making a negative amount, that means the company is losing money. Hopefully this is a positive. So if you put this in your calculator, you run it all through, you get 303.35. So what does this mean? It means they expect to make money on average from each person. So it's not that they're making this amount from each person, it's that sometimes they pay out and most of the times they collect here at the end, 99% of the time. On average, they're going to be making about $303 per person. So that means they're making a profit. And that's how insurance companies would work. That's how they determine actually if they need to raise rates or lower rates so they can cut you a deal. They work out the expected value. Question 5 is just similar problems with expected values. So can we find the expected value for these different situations? When you roll just one dice, okay, what values can you get? Are they all equally likely? What's the expected value of one dice roll? Well, we can roll a 1 or a 2 or a 3, a 4, a 5, or a 6. Those are the only possible outcomes. And then we have to multiply them by their probabilities, which would be 1/6. 2 will happen 1/6 of the time. 3 will happen on just 1 out of the 6 faces. And actually that's what the probability is for all of these numbers, 1/6. If you had a different dice, like a 4-sided dice or an 8-sided dice, these numbers would change to represent how many faces there are. If I put all this in my calculator, I'm going to get 3.5. Now, if you think about what you can and can't roll on a dice, you can roll a 3 or you can roll a 4. You can't roll in between them. You can't roll a 3.5. But that's what we would expect to get if we averaged out all of the rolls. And that kind of happens because all of the probabilities are the same. If you average those numbers, guess what you get? You get 3.5. So the regular average and the expected value, the weighted average, turn out to be the same. So you can expect to roll a 3.5 on average with one toss. So if we did this thousands and thousands and thousands of times and we averaged all of the results of every single toss, that number, that answer for those thousands of tosses would be about 3.5. While you're here, just go ahead and cross off B and C. Those problems don't really pertain to the expected value. They were just trying to get you to think outside of the box and to consider some of the different options that you might get. A little bit of critical thinking skills. If you flip to the next page, our next idea is talking about the law of large numbers. All that is if you repeat something many, many different times, and each trial is independent of the last, so that means you're just doing it over again and you're not having the past affect it, the mean of those observed outcomes will approach the expected value. If we go back here to our lottery problem, if we just bought one lottery ticket, chances are that we're just going to win $0 here in the end. We would have to play this lottery many, many times in order to probably win once or maybe twice, and the average over all those times would be close to 50 cents. So if we do it many times, that average is going to get closer and closer to the expected value. Same thing here with the dice toss. If we just toss one dice, maybe we get a 1 or maybe we get a 6, which isn't close to the expected value. But if we did this thousands of times, the law of large numbers says that we would get close to the expected value. So question number 6 says, a certain brand of cereal comes with 1 of 5 prizes in each box. The company that packages the cereal says that there's an equal chance for any of the prizes to appear in a given box. Assuming that that's true, how many boxes of the cereal would you expect to have to buy in order to collect all of the 5 different prizes? Well, the very least would be 5. That's if you collected a unique prize in each box, and that would be as efficient as you can be. Realistically, though, we're probably going to have to buy more because we'll sometimes get duplicates. So we might, on the third box, get the same toy that we got on the second or the first. So maybe it's going to take us 8 or 9 boxes. That's kind of what we're trying to see here, and we're going to perform a simulation. So using a random digit table or even your calculator, we're going to generate the numbers 1 through 5. So 1, 2, 3, 4, 5. Each one representing one of the different prizes in those boxes. So you have to get 1, 2, 3, 4, and 5. You want to get each one individually. So you have to keep going until all 5 of those would be crossed off. We're going to go ahead and do 5 trials and record our results to see if there's any pattern to those results. Now, in order to make this a little bit more efficient, we don't want to just use the digits 1 through 5. We're going to use the digits 0 through 9 because we can use twice as many. If we pair 0 and 1, maybe that's the first box, 2 and 3, 4 and 5, 6 and 7, and then 8 and 9. Those would represent maybe the first box, second box, third box, fourth box, and the fifth box. That way we aren't wasting the other digits. So down here in the table, you're going to do a first trial. So if you get your random digit table out and you point at a line, if we are working through and we cross one off twice, we have to keep on going until we get this last one, and then everyone is crossed off. So if I was counting that, this would be 1, 2, 3, 4, 5, 6, 7, 8 different trials, or 8 different boxes of cereal. All right, then I would go ahead and do this again. So point at a different line, and then you're trying to get those 5 boxes of cereal, those 5 unique combinations, and maybe this time it takes me 14. When I did this, I got 21 boxes, then I got 9 boxes, and then 15 boxes to get all 5 of those toys. 7 was my most efficient, so I only had 2 duplicates, and then my last one was 12. And again, you can pick anywhere on your random digit table, but it goes a little faster if you go with this route instead of with going 1 through 5 only. So if you are going to put this on your scatter plot, which as a class I would like to do, 12 happens, and 12 would be right here. So I'd put my dot on 12. Then 7 occurs right there. 15 is here. 9 is over here. And then the last one, which is 21, occurs down at that spot. So as we continue to get more and more people, these dots are going to start to form patterns. where we have the most dots is probably going to be close to our expected value, because the more repetitions that we use, the closer we will get to that expected value. So if there's a big clump of dots, maybe like right in this frame, our expected value is probably pretty close to this. Calculating the expected value actually turns out to be a little bit harder than I thought. So we can estimate by wherever the big clump of dots is, wherever there's a congregation of dots, that number is probably going to be where the expected value lies. It might be down here towards 5, it might be maybe towards 9 or 10. Okay, but wherever there's a big clump of dots, that's where the expected value starts to stay due to the law of large numbers.